We now turn our attention to including the enthalpies of solution and hydration in this topic of lattice enthalpy. So first of all, let's look at some definitions. So standard enthalpy of solution is the enthalpy change when 1 mole of solute is dissolved completely to form a concentration of 1 mole per decimeter cubed. And the standard enthalpy of hydration is the enthalpy change when 1 mole of gaseous ions become hydrated, and again that's measured under standard conditions. Those definitions actually mean in reality. So first of all, solution is an example of dissolving sodium chloride to make a solution of 1 mole per decimeter cubed sodium chloride, and this would represent the hydration of sodium ions, and this is the hydration of chloride ions. So we can put these new enthalpy changes into a Hess cycle, and we can relate them to our lattice enthalpy. So those are the ones that we have so far, and there's our lattice enthalpy of sodium chloride as well, and we're going to put these all together into a Hess cycle. And the most energetic species out of the ones we have will be the gaseous ions, and of course those combining to give us the solid is the lattice enthalpy, and we can work our way downwards the other side using from the hydration of the two ions to give us the ions in solution, and then the difference between going from sodium chloride solid to the aqueous solution is of course standard enthalpy of solution. Now lattice enthalpy, as we know, is a very large exothermic value, as are the enthalpy of hydrations are both large and exothermic values. So that means that our standard enthalpy of solution is either a very small endo or exothermic value dependent on the relative values of the lattice enthalpy and the hydration enthalpies. It's going to be balanced depending on which of those sides is the most energetic. So we can work out the enthalpy of solution by using Hess's law, and it will be equal to the hydration enthalpies minus the lattice enthalpy. So if the two hydration enthalpies are more exothermic than the lattice enthalpy, then the enthalpy of solution will be exothermic, as we've shown here. However, if the lattice enthalpy is more exothermic than the two hydration enthalpies, then the cycle will change, and our standard enthalpy of solution is now endothermic. And that is in fact the case for sodium chloride. If we look at the values we have there of lattice enthalpy and our standard enthalpies of hydration, our solution enthalpy is worked out by the hydration enthalpies minus our lattice enthalpy, and that comes to overall a difference of 1 kilojoule per mole, and that's a positive figure. So we know that the enthalpy of solution is equal to the hydration enthalpies minus the lattice enthalpy. The hydration enthalpy gives us a measure of the strength of the attraction between the ions and water molecules, whereas the lattice enthalpy is determined by the strength of the attraction between the oppositely charged ions. So if the strength of the attraction between the ions and water is greater than the ionic bond strength, then the enthalpy of solution is exothermic. However, if the ionic bond strength is now greater than the strength of the attraction between the ions and the water, the enthalpy of solution is endothermic. So it's a very fine balance between those two large negative numbers. Stronger lattices, so those with more exothermic lattice enthalpies, occur when we have small ions that are highly charged. We have ions with a high charge density, and they pack closely together and have stronger forces of attraction between them. And we know that the enthalpy of hydration follows a very same pattern. As we increase the ionic charge and decrease the ionic radius, thereby increasing the charge density, this leads to a stronger attraction for the water molecules. And so, as they both will become more exothermic as our ions become smaller and more highly charged, and therefore it's very difficult to predict whether the solution enthalpy will be endo or exothermic.